All right, we're going to close out this chapter by looking at how we solve trigonometric equations. So far we've been just working with identities, equations that are true for all angles, and we're going to switch gears a little bit and look at an equation that's not an identity, so not true for all angles, and just trying to figure out for which angles is this equation true. We're going to be using algebra and the trig identities to help us rewrite equations and get it to a point where we can find the angle. For the most part, these equations will usually have many solutions, maybe infinitely many, but we're only going to find the solutions for one go around the unit circle, so from 0 to 2 pi or 0 degrees to 360 degrees. We're going to start with a simple one where we're going to want to solve for theta, where theta is between 0 and 2 pi. So right off we know, and this is true for probably most equations, we want radians, right? They're telling us that here, that we want our answer to be in radians. If they wanted it in degrees, they would have said between 0 degrees and 360 degrees. The way that we're going to solve these equations is first solve it for a trig function. If I know the value of a trig function, I could either use an inverse function or, a lot of the time, the unit circle to find the solutions that we're after. So, for example, here I'm going to start by adding 1 to both sides. And we have 2 cosine theta is equal to 1. If I now divide both sides by 2, I get cosine theta equals 1/2. Now, a lot of the time when we're working on these equations, the values that we'll find, right, so we said cosine theta is 1/2, that's going to be, a lot of the time, one of those convenient values that we can find right on the unit circle and get a nice exact answer. So if we look on the unit circle, if we're looking for places where cosine theta is equal to 1/2, that means we want the angles where the x-coordinate is 1/2, positive 1/2. We could see that happens in the first quadrant here at pi over 3, and also in the fourth quadrant at 5 pi over 3. And there we are. Now, if we didn't think about using the unit circle, we could still solve this by saying, look, if cosine theta is 1/2, that means that theta is arc cosine of 1/2. We have to understand that if cosine theta is 1/2, that there's an answer in both the first and fourth quadrants. And find both of those. You know, we get our reference angle and then find the angles that we're looking for. Since one of ours is in the first quadrant, I'm just going to use arc cosine of 1/2 in my calculator, making sure my calculator is in radian mode. We get 1.047. And then in the fourth quadrant, that's 2 pi minus this reference angle. That's 5.236. So these are our two answers. And if you, you could see that these are equivalent, right? If I take the calculator and I just do pi divided by 3, there's our 1.047. If I do 5 pi over 3, there's my 5.236 value. For the most part, I think in these examples and most of the exercises, we can do this just by using the unit circle, and that's how I'm going to go about it. So let's do another one. We want to solve for x, where x is between 0 and 2 pi, so one go around the circle. One thing that makes this problem a little bit trickier than the last one is that there's more than one trig function. I really want to be able to boil this down to statements where I just can find the value of a single trig function and then use the unit circle. So I'm going to start actually by using the Pythagorean identity to rewrite cosine squared theta. So cosine squared theta using Pythagoras is 1 minus sine squared x, and then minus sine x minus 1 equals 0. This is an equation we're working with. We're not proving an identity, so we are kind of maintaining equality throughout, carrying this equal sign down. I'm going to do some algebra now. I'll distribute that 2, so we have 2 minus 2 sine squared x minus sine x minus 1 equals 0. And combining our constant terms, we have a minus 2 sine squared x minus sine x plus 1 equals 0. Now what I'm going to do is I'm going to multiply both sides by a negative 1, and I'll tell you why in a second. If we multiply both sides by negative 1, the left side, we're just going to switch all the signs, so 2 sine squared x plus sine x minus 1, and the right side is still equal to 0. It might not be obvious at first, but this is a quadratic equation. It's just a quadratic equation where a variable is sine x. We could solve it like we solve other quadratic equations. In particular, I think we can solve this one by factoring. And that's why I multiplied by negative 1, because it's easier for me if I have a positive leading coefficient, so making this a positive times a positive 2 sine squared x in the beginning. So let's try to factor. To get a 2 sine squared x, I know I'm going to need to multiply 2 sine x by sine x. We have a negative 1 at the end, so I know I need a 1 and a 1, but one's going to be positive and one's going to be negative. And the one that works out to give us the plus 1 sine x in the middle is if we have 2 sine x minus 1 and sine x plus 1. You could double check that, but that'll work out to the quadratic above. So now I have a product that's set equal to 0. So we already know what to do in this situation. We learned about it when we were solving quadratics in the last semester. I'm going to set each factor equal to 0, so 2 sine x minus 1 equals 0, or sine x plus 1 equals 0. I'm going to just solve each one of these. I'll start with the first one. If I add 1 to both sides, then 2 sine x equals 1, and dividing by 2 gives us sine x equals a half. And if sine x is equal to a half, then x equals, let's go to the unit circle. Now we're looking for, on the unit circle, where is the y coordinate equal to? Positive 1/2. That happens here at pi over 6, and over in the second quadrant at 5 pi over 6. With this other equation here, sine x plus 1 equals 0, we're going to just subtract 1 from both sides. That means that sine x is equal to negative 1. And there's only one spot where sine is equal to negative 1. The y coordinate is negative 1 only at the very bottom of the circle, so that's at 3 pi over 2. And there's our solutions to this equation. Okay, so one way in which these equations can be challenging is if it involves more than one trig function, and then we just want to use an identity to try to see if we can't get it to involve just one trig function, an identity and maybe some algebra. In the next example here, we do just have a single trig function, and that's great. However, note that the arguments are different here. Right? In one of these cosine functions, it's x over 2, and in one function, in the other cosine function, it's x. So that's going to make us just slow down and think about how we can write it in terms of a single trig function of one variable, of the same variable. Okay, so cosine of x over 2, if we start by using the half angle identity, I could rewrite cosine of x over 2 as plus or minus the square root of 1 plus cosine x all over 2, and that's equal to 1 plus cosine x. Now I have the same function, with the same argument inside, and that's progress. I've got this radical, but we know how to solve equations with radicals. I've got the radical that's already isolated on one side, and that means that I could square both sides and get rid of the radical. As it happens, when I square both sides, I'll also get rid of that plus or minus business. And then we get 1 plus cosine x all over 2 on the left side. And on the other side, we're going to FOIL this out. We're going to do some algebra. And we get 1 plus 2 cosine x plus cosine squared x. Before we go any further, I just want to point out that when we used the half-angle identity and rewrote it, we turned it into an equation with radicals. So we're going to have to be careful. You'll remember that when we solve equation with radicals, it's possible to get extraneous roots. So when we solve these equations, we're going to check our answers at the end in the original equation to make sure that they work out okay. All right, let's clear denominators. Let's multiply both sides by 2. So 1 plus cosine x is equal to, I'm gonna distribute the 2, and I'm also gonna just start with my highest power of cosine. So 2 cosine squared x plus 4 cosine x plus 2. That's just a habit that I'm in to write the highest power first. And this is another quadratic like the last one. It's a quadratic in cosine instead of sine. I'm going to gather all my terms on one side, so I'm going to subtract 1 and subtract cosine x. So we get 0 is equal to 2 cosine squared x plus 3 cosine x plus 1. And like the last one, this will factor. You can convince yourself of this by kind of working it out, or maybe you want to pause the video and see if you can't find the factorization yourself before I tell you, but it'll factor as 2 cosine x plus 1 and then cosine x plus 1. That'll work out to give us the plus 3 cosine x in the middle. All right, so now I'm going to come over here. We have a product equal to 0. We're going to just proceed by setting each factor equal to 0. So 2 cosine x plus 1 equals 0, or cosine x plus 1 equals 0. I'll start with the equation on the left first. If we subtract 1 from both sides, we get 2 cosine x equals negative 1, and then dividing by 2 tells us that cosine x is negative a half. And there are two values, two angles for which cosine is negative a half. I'm going to go to the unit circle. I'm looking for where the x coordinate is negative a half. That happens here at 2 pi over 3 in the second quadrant, and over here in the third quadrant at 4 pi over 3. With this other equation, we find that cosine x is negative 1, and there's only one spot where cosine is negative 1. That's at the extreme left, over here at pi. So we have these three answers, but remember, again, we turn this into an equation with radicals. It's possible to get extraneous roots. So we're going to check each of these in the original equation up here. This cosine x over 2 equals 1 plus cosine x. So here's our equation. So we'll start with 2 pi over 3. If x is 2 pi over 3, that means that x over 2, half of that, is pi over 3. And now what I'm going to check is the left side, cosine pi over 3. Is this equal to, put a little question mark here, is that equal to 1 plus cosine of 2 pi over 3? So cosine of pi over 3, you can use the unit circle or your calculator. Cosine pi over 3 is a half. 1 plus, on the other side, cosine of 2 pi over 3, cosine of 2 pi over 3 is negative a half, and in fact, 1/2 is equal to 1/2. So that checks out. For the angle x equals 4 pi over 3, that means that x over 2 is 2 pi over 3. So now this equation looks like cosine of x over 2. Cosine of 2 pi over 3, is this equal to 1 plus cosine of 4 pi over 3? Well, cosine of 2 pi over 3 is negative 1/2. We want to know, is this equal to 1 plus, let's see, cosine of 4 pi over 3 is negative 1/2. And as it turns out, that's not the case, because negative 1/2 is not equal to 1/2. So far what we've done is we've deduced or concluded that 2 pi over 3 is a solution, but 4 pi over 3 is not. We've got one more to check. We're going to check pi. If x is equal to pi, that means that x over 2 is pi over 2, and our equation looks like cosine of pi over 2, and we want to know, is this equal to 1 plus cosine of pi? Well, cosine of pi over 2 is 0. 1 plus cosine of pi is negative 1, and that is in fact equal to 0, so that checks out as well. So there are two solutions to this equation in one go around the unit circle. Okay. All right, we've got one more example to finish out this chapter. We're going to solve for theta, where theta goes from 1 to 2 pi. That's our standard set of instructions here. We want theta to go one go around the circle. I'm kind of pointing that out right now because our equation involves tan of 2 theta and cotan of 2 theta. Well, to start out, I mean, we have two different functions, but we can deal with that. We'll be able to write it in terms of a single function. The angles are the same. They're both 2 theta. I just want to point out that if theta is going once around the circle, we have to let 2 theta go twice around the circle. And once we find those values for theta, it does say solve for theta. So once we find those values for 2 theta, we're going to cut them all in half to get the values for theta that make this work. So let's see, this means that 2 theta is between 0 and 4 pi. Okay, so I'm going to start just by rewriting the cotan of 2 theta as 1 over tangent. So we have tan 2 theta minus 1 over tan 2 theta equals 0. Now I have an equation with fractions. We know how to handle an equation with fractions. We multiply by the LCD to clear denominators. So we're going to multiply both sides of this equation by tan of 2 theta. And when we distribute this on the left side, we get tan squared 2 theta minus, let's see, in the second term it'll just cancel, so minus 1, and we still have 0 on the other side. Okay, so this is another quadratic. It's a quadratic in tangent, but this is a difference of squares, so we could factor it as tan 2 theta plus 1 times tan 2 theta minus 1. That means that we're going to set each of these factors equal to 0 again, so tan 2 theta plus 1 equals 0, or tan 2 theta minus 1 equals 0, which means that tan 2 theta is either negative 1 or it's positive 1. So I just want to figure out where is tangent equal to 1, where is tangent equal to negative 1. So tan is equal to negative 1, and we could do this on, using the arctan function, but Remember that tangent is equal to sine over cosine. So the value of tangent will be 1 precisely when sine and cosine are equal to each other. And there'll be -1 when sine and cosine are equal but just different signs. So tangent is equal to -1. Tan of 2 theta is -1 when 2 theta is, let's look at the unit circle, that happens at 3 pi over 4. Sine is positive root 2 over 2 and cosine is a negative root 2 over 2. And then over in the fourth quadrant at 7 pi over 4. And tan of 2 theta is +1 when sine and cosine are the same value with the same sign. So that happens at pi over 4, and again over here in the third quadrant at 5 pi over 4. Alright, so we have these initial values for 2 pi. Now when we found these values, we just looked one go around the circle. Remember that if theta is going to go from 0 to 2 pi, 2 theta has to be allowed to go from 0 to 4 pi. So the way we're going to find the other values for 2 theta is to add a full revolution to each of these values. So we're going to add 2 pi to each of these values. And when we do that, let's see, 2 pi is equal to 8 pi over 4, so we get 11 pi over 4. 8 pi over 4 plus 17 pi over 4 is 15 pi over 4. Over here we get 9 pi over 4. And 5 pi over 4 plus 8 pi over 4 is 13 pi over 4. Now finally, these are all the values for 2 theta. We want to solve for theta, so to get values for theta, we're going to divide each of these 8 values by 2. So theta is equal to, let's see, 3 pi over 4 divided by 2 is 3 pi over 8. When you divide a fraction by 2, there's 2 ways to do it, right? You can either cut the numerator in half, which for us is not much of an option just because they're odd, or you can double the denominator. So that's what I'm going to do. I'm just going to double the denominators for each of these fractions. So 3 pi over 8, 7 pi over 8, pi over 8, and 5 pi over 8. And down here, we get 11 pi over 8, 15 pi over 8, 9 pi over 8, and 13 pi over 8. So there are 8 solutions for this equation in theta.